I know the, oh yes, the must.
Okay, which one? Okay. Does anybody mind if I stand?
Yeah.
And, okay, perfect. Yeah, perfect. And there we go. Yeah, perfect. Maybe okay. Everybody can see okay? Good. So I went to the University of Illinois, and since the last 12 years, I've lived in Houston, Texas. And the interesting thing about Houston, Texas is there are three main languages in Houston. The first is English. The second is Spanish, because of Mexico, very nearby. And the third is Vietnamese. It's true. And there are many, many Vietnamese people. And so because of that, we have excellent Vietnamese restaurants. But nothing compared to here in Hanoi. So it's been excellent. Okay, so what I would like to talk a little bit about is some of what I think are the exciting areas that are being researched right now in signal processing. Some of these things I'm doing, some of them I'm not doing. Some of them Professor Go is doing. But I think it will give you an idea of the trends, the directions that DSP seems to be going. And I will also do my best to answer questions and try to guess what the future is going to be like, just like Sydney refused to. Okay. So the thing I'm going to talk about through the talk is that signal processing is fundamentally a quest or search for structure. Some kind of structure in signals that you're trying to either model or extract or process, or compress, or remove, okay? And so what I'm going to do is talk about some of the different kinds of signals that are emerging as important application signals, the kind of structures that are in those signals, and what people are doing to try to process. Does that sound okay? And you can just interrupt me anytime, except for Professor Go. Not allowed. Okay, so this is old school signal processing, right? Analog signal processing, right? This is Sidney Burris style, early Sidney Burris style signal processing, when everything was done in analog and in terms of voltages and currents, and the signal processor was really a circuit designer. There was really no difference between the two, okay? And what we're emerging into, of course, is a world where the first thing that we do with every signal is what? What's the first thing we do? You sample, right? We sample signals because we can put things into the digital domain, discrete time domain, and then we can use a computer, right, to do the DSP, or the processing. So really, DSP people have stopped becoming like analog circuit designers, and they've become more like computer scientists or mathematicians, right? Well, they're all mathematicians, but it's become more discrete time instead of continuous time, right? If you nod your head, I'll just keep going. Good? You agree? No? You disagree? Anybody disagree? So really now, digital signal processing you can think of, if you draw a Venn diagram, is really at the confluence of three areas. Information, the kind of information that we care about in signals, whether it's your favorite song or not your favorite song, or whether the song is Minjo's voice or my voice, that's information. Communication is very important. Moving information from one place to another is critical. And the third aspect is computation, right? And now we do signal processing on computers, digital computers, and DSP is really at the confluence of these three areas. So I'm going to talk about some different applications today in the information area, communication area, and computation. Okay, so DSP really is sampling and then some kind of computer program. So I'm going to talk about different kinds of signals, and the important thing, I think, these are what I think are the important themes of signal processing that are emerging. The first is we're moving from simple one-dimensional signals, like time signals, like my voice, like your heartbeat signal, right? Or communication signals, we're moving to higher and higher dimensions. More and more important problems with imagery, digital camera type problems, radar type problems, three-dimensional kinds of problems, video processing, right, for not only television but high-definition television. There are all kinds of interesting problems around high-definition television. Volumetric data, so signal processing on cubes of data, volumes, like a volume inside the Earth. Tons of research going on in that, and especially with the price of oil at about $78 a barrel, tremendous interest now in seismic data. Okay, does Vietnam have much oil?
Yes, we do have our ocean.
You're very lucky. Okay, you're very lucky. Okay, what about gas?
I don't know. Do we have gas? We have gas.
Okay, good. And then, but think, so everyone's comfortable with one-dimensional signals, right? They're signal, I can draw a picture too, but they're signals that vary with a time variable, right? An image has a space variable, an X and a Y. Volumetric data has three dimensions, X, Y, and Z. But now think in terms of four-dimensional or five-dimensional data. So I'll talk about data, and I know Professor Do is working on problems that involve up to seven-dimensional data. Okay? Very, very important problems relating to things like three-dimensional television for the future. Okay? And just think for 1 second about sampling. If I sample a signal 1,000 times a second, is that very fast? Not so fast. Is that fast enough to capture my voice? Is it? Not very well. Maybe very poorly, but not very well. Okay, because I don't have a deep voice. Right? If I was very light, I would have a deep voice. But now think of sampling an image 1,000 times on a side. How many pixels do I have now? 1,000 this way, 1,000 this way gives me how many samples? 1 million samples. Is that okay? Can we do that? Can we build systems that do that? Sure. Who has a camera phone? Anybody have a telephone? A camera on your telephone? Yeah, some of you do. Well, that's at least 1 megapixel, right? Probably 3 megapixels. Okay? But now think of one of these crazy MINDO data sets that's 7-dimensional. Okay? And think of sampling 1,000 on a side. Okay? How many voxels of data do we have now? 10,000 million, 10 to the 21. Huge, right? Do you think we could even build a computer that would store all of this information? There's no way, right? So when we push to higher dimensions, we're going to be pushing towards data that is harder and harder and harder to do DSP on. And so that means more and more research is required. But these are very important problems that people are going to care about or do care about already. Okay, so that's the first, high dimensions. The second is geometrical data. I mean by that data that has some geometry to it. And I'll make that more clear in a second. Another very important theme is distributed algorithms. Okay, the things that Sydney talked about today with wave transforms, and probably most of the things you talked about in the class up to now, have been what you would call centralized processing, where you take the signal, you put it in a computer, and you do processing on it, right? If you have many signals, you bring all of them to the computer, you do processing on them, and then you get the answer. With distributed signal processing, what you try and do is do processing in many different places at once. Okay? And then somehow do the processing independently at different places at once, and then try to combine to get the answer. Have people heard of peer-to-peer networks? People heard of these? Okay, so ideas of using peer-to-peer type ideas are going to be very important. I'll talk about sensor networks